name is Santiago Gollarza. Thank you for having me here today. I am a dual enrolled 11th grade student at Florida Atlantic University High School. And Christina here.
Hi, my name is Christina Koyama. I am in 9th grade at American Heritage School, and I've been with WolfSat for 5 years.
And I've been with the Wolfpack for about 6 years. And today, we'd like to talk to you about the WolfSat-2 mission, which is basically, we want to measure the viability of a directly injected wooden chassis CubeSat. So I'll explain what that means a little later, and so that's basically what I'm going to talk about. So, firstly, WolfSat-2, what it really is. It's a 1U CubeSat designed and built by the Wolfpack CubeSat development team. A 1U CubeSat is basically just a CubeSat which has the dimensions of 10 centimeters by 10 centimeters by 10 centimeters. It's basically a very small satellite which you can really use for a lot of applications. So this mission will launch in 2027 from Hokkaido, Japan on an Interstellar Space Technologies Zero rocket. And one of the benefits of this is that it's going to be directly injected into the atmosphere instead of just being let go in orbit. So this is going to be the 5th WCBT small sat which we built since 2018. So that's basically our flight heritage. We've had about 4 satellites beforehand, with our most recent one that we're going to launch later this year being WolfSat-1. And this team, the WCBT, is primarily composed of students from ages 10 to 18 from Florida, a couple other US states, Ireland, Norway, and even Israel. It's a very far-reaching group that is overall composed of all students ages 10 through 18. So the Wolfpack team is basically, we work in a structure of smaller teams which design, build, test, and fly CubeSats, and we simultaneously, while we do that and get the real world experience, we develop this sort of professional literacy and soft skills that we will eventually use in the workforce. For example, actually yesterday, a couple members of our team were on Capitol Hill talking with legislators, and overall basically just operating with their main topic, which that being law and public speaking. So a couple key features of our team is that our students take leadership and accountability over their own projects and their own topics. And there's a couple of technical subsystem divisions. For example, some members will work more on engineering, some members will work more on biochemistry, and some members will generally can even work more with public speaking. Alongside that, we have our long duration project ownership where students can work on projects for up to a couple of years. For example, we have a couple of students who have been working on the WolfSat-1 project since a couple of years ago, and we're launching it now. And they've been working on it every step of the way. Alongside that, we have our peer mentorship where a lot of older students will help out younger students to achieve goals together and overall share their professional experience which they've learned. And of course, we have our real deadlines and consequences, which you wouldn't get in a simulated environment. We actually sign contracts and have dates that we have to work with actual professional groups. And so as a result, our contracts are non-negotiable and we have to submit, which is something that you don't really get in other schooling environments. So our mission, the WolfSat-2, has a couple of details which make it a lot different from other satellites. So specifically, we want to test birchwood as a sustainable chassis material. So we got this idea from a Japanese satellite developed by Kyoto University called LignaSat-1. And the main reason why we're doing this is because we were interested in the sustainability of a wooden satellite. We don't really know the repercussions of large amounts of aluminum in the atmosphere after the end of life of a satellite. And additionally, we have the problem of space debris, which we've heard in many other presentations, such as the presentation that we heard earlier. So a couple key areas that we want to study in our satellite are thermal management. We want to see how it manages heat. We want to see sensors, which manage, our sensors are going to manage the tension and strength of the wooden chassis. We want to use CAD modeling to see how we can actually model this using computer-assisted design. And we're using orbital decay modeling to measure how exactly it's going to look in orbit. And overall, we're developing a compact design using our 1U CubeSat limit, as I mentioned, that's our 10 centimeter limit, and that helps us create a sort of limitation for compact design for teaching. And eventually, we want to evaluate whether or not this structure can actually survive in very low Earth orbit or thrive and technically be used for future precedent. And now I'm handing it off to Christina to discuss a couple more details of the project.
So, our main material of our CubeSat is going to be birch wood. We've been writing down pros and cons of several different types of wood, but we decided that birch was going to be the most suitable for going into space, and our walls are going to be 6 millimeters in thickness. An alternative material that we could use is birch plywood if we have any sourcing challenges. Our 4 walls of the CubeSat are going to be using dovetail joints to be joined together, and then top and bottom are going to be using preferably rabbet joints with approximately 8 dowels on each side. The rails will have a wooden core with aluminum a layer around it so that it's more compatible with the interior of the rocket, and so it can give some more structural stability. So the sensors. The sensors will be used to monitor the structural health during the orbital conditions. So we'll see whether the wood inside will split or crack or something. And several sensors that we have selected is BF353AA electrical resistance strain gauges and the piezoelectric sensors. These sensors will be used to specifically track the stress, strain, and torsion during vacuum loading and thermal cycling. These sensor hardware are made sure to be within the CubeSat mass, power, and downlink limits. So this is a model that one of our teammates have made of the orbital decay. He employed the Euler integration to estimate our mission's lifetime. So this model has included drag, scale, height, and gravity changes, and solar activities by averaging different density conditions. Based on this modeling, we have expected the life expectancy to be around 11 more days, so about 22.89 days. But the reason why our life expectancy is so short is because our CubeSat is going to be released into very low Earth orbit. So we have only a bit of time to work with it. And so our team has decided to use passive approaches for attitude determination and attitude control via neodymium magnets. It's very suitable given the altitude of our orbit and the mission parameters. Our team is going to be using Python to model orbital heating and cooling, and conductivity, absorbance, and emissivity were considered. The surface protection priorities listed in descending order is the atomic oxygen protection, UV resistance, and tuning of absorption.
So for our project, we have a couple of steps that we want to go over for our future, basically. We want to test, firstly, our prototype designs using vibration testing on a vibration table, and we also want to do a thermal bakeout test in order to see how it holds up under high temperatures or low temperatures. Furthermore, we want to integrate our payload, our satellites, and our overall payload, which we're going to need for sharing our data back home. We want to see using our chassis and bus. That's what we want to do now, so we want to integrate our bus into our chassis. And then other than that, we want to debug and test our software code in order to see what kind of qualities we can get from our software. And then overall, our WolfSat-2 mission represents the second ever CubeSat with a wooden structure to be launched, but it does also represent the first CubeSat to be directly injected into orbit other than just launched directly. And overall, this mission, other than that, has also served as pretty authentic and hands-on aerospace training for pre-college students. As you can see, this mission has helped students with both mathematical modeling, engineering modeling, working with material science and public policy even, and even with communication between different associations. As you can see, we were launching it with a CubeSat team in Japan, and obviously that takes a lot of determination and effort in order to get to launching a CubeSat in such a situation. So thank you for coming to our presentation today. If you have any questions, let us know. Thank you for having us today for our presentation.
We're very happy that you listened to us today.